Hello and welcome to this last online class for CE 105. So today we are going to talk about toughness and strength of glasses. So we had two previous chapters on the stiffness of glasses, which is the resistance to reversible deformation. So you apply a load and you remove the load, the glass deforms and then recover its initial shape. And in that case, the stiffness characterizes how much the glass will deform in a reversible fashion. Then we had another chapter on hardness, which is the resistance to irreversible deformation, when you apply a load that the material deforms but doesn't go back to its initial shape, so which is what happens when you have an indent or a scratch, a permanent deformation of the glass surface. And today we are going to talk about the toughness and strength, which characterize both property characterize the resistance of glasses to fracture, to breakage or crack propagation. So let's first talk about the strength, which is a first material property that is very useful to characterize how resistant a given material is to fracture. So just to make it clear one more time, although in common language those terms like stiff, hard, tough, etc. are commonly used and pretty much have the same sense, in mechanics those terms have very different meaning. For example, here the stiffness characterizes the deformation of the bridge as this individual is walking on it. In that case, the stiffness characterizes the instantaneous deformation of the bridge, assuming that the bridge is going to go back to its initial shape after the guy is done working on it. So this deformation, this deflection of the bridge, which is reversible, is characterized by the stiffness. If the bridge is stiff, then it will not deform much. If it is not stiff, it will deform a lot. But this doesn't have anything to do with the propensity for fracture. You can have something that is very stiff but that is not very easy to break, or you can have a material that is very stiff but that can break very easily. So those properties do not mean the same thing, and they might not be correlated to each other. We have seen last time the hardness. The hardness would characterize the ability of this bridge to resist permanent deformation. For example, once this guy is done walking on the bridge, if the bridge remain permanently deformed like this, then this is captured by the hardness of the material. And finally, the strength is characterizing the resistance to fracture. So if the bridge is breaking, that is to say, if it starts to be divided into different pieces, if there is some crack propagating within the material, then this is a fracture phenomenon. Fracture phenomenon is an irreversible phenomenon, but it's different from hardness, so it's different from stiffness. So this is characterized by the ability of a material to resist fractures. This is what is going to be captured by the strength, by the toughness, or by the fracture energy, which are different properties which characterize different aspects of the ability of a material to resist fracture. So how do you measure strength? Usually to measure strength, what you do is that you measure the stress-strain response of a material by applying a uniaxial tensile test. So you take a given material and you apply a stress, a given stress. You apply, for example, a given force per unit of surface. So you apply a stress along the longitudinal axis, and you apply usually a tensile stress if you want to measure the tensile strength of material. Typically, material will break more under tension than under compression, so usually we are more interested in the tensile strength. Then you plot the corresponding stress that you need to apply to deform the material. So this is the stress that you apply, the force per unit of area, and you have the corresponding strain, which is the relative deformation, how much the material is going to elongate after you apply the given stress. Then based on that, you can get the stress-strain curve, which can be either linear like this for a brittle material, or can show a more complicated pattern if you have a more ductile material. So this one is for the case of a brittle material. This one would be for a material that shows some ductility, so a more ductile material. And then the strength is defined as the stress that you need to apply to the material to break it. So you look at what is the stress that is applied when the material breaks, and that gives you the strength. So here you would read the strength for a brittle material. If you have a ductile material, you can have potentially two kinds of strengths. You can have here what is the maximum strength, maximum stress that the material can sustain before breaking. So this gives you the tensile strength. Or you can look at what is the stress at the point of fracture, which might be different from the tensile strength. This one gives you the breaking strength, which are two different properties that don't mean exactly the same thing, but are still pretty close to each other. In both cases, the strength gives you first, the strength has the same unit as a stress, so the strength will be expressed in Pascal, or more commonly in gigapascal or in megapascal, depending on the ability of the material to resist fracture. So it has the same unit as a pressure or as a stress. It's a force per unit of area. It gives you what is the maximum stress that the material can sustain before breaking. So in the case of glasses, we will be typically in this configuration. Glasses are typically brittle material, which means that in the case of glasses, typically the stress will increase linearly with the strain until you reach a strength point where suddenly the material will break. So if you consider glasses, we know that glasses are very brittle material. They break fairly easily. It's fairly easy to break a window glasses or a glass recipient, a glass container. Those are materials that typically break quite easily, at least more easily than steel or other types of metals. That being said, if you look at what would be the maximum theoretical strength of glasses, for example, if you look at the atomic scale, the atomic network that constitute glasses, and you look at what is the force that you would need to apply to separate a pair of atoms from each other, then you find that this maximum theoretical strength is on the order of 10 gigapascal, which is a very high value of stress, which corresponds to a very intense force concentrated over a very small area. So this tells you that the glasses have a very high maximum theoretical strength. So the question is, why in practice most glasses will break at stress value that are much lower than this maximum theoretical stress? Indeed, if you look in practice at most glasses and what are the typical order of magnitude of their strength, typically you observe that it's very far away from the 10 gigapascal, which is the maximum theoretical strength. Typically, for most glass products, you have a strength that is more on the order of megapascal. So for example, for most glass products, you have a strength that is between 14 to 17 megapascal. You have, depending on some other material, you might have a slightly different strength value. You can see that when you look at fibers, typically fibers have much higher value. Fibers can have a strength that is on the order of 0.7 to 2 gigapascal, which starts to be closer to the maximum theoretical strength that glasses may have. Just out of comparison, the strength of metal is typically on the order of a few hundreds of megapascal. The strength of concrete is on the order of a few thousands of megapascal. So typically the strength of glasses is pretty much on the same order of magnitude as the strength of concrete, a few tenths of megapascal. But this is very, very far away from the maximum theoretical strength of glasses. So the question is, what is limiting the maximum theoretical strength of glasses? Why is their strength in practice so low as compared to their maximum theoretical strength? So the difference between the theoretical strength of a given material and the real strength is not something that is only specific to glasses. For example, here, if you take a look at a selection of different material and you look at their theoretical strength, which is typically on the order of several gigapascal, and their real strength, the strength that you actually measure in practice for those materials, which is typically going to be on the order of megapascal, so smaller than the theoretical strength. What you can check is to calculate the ratio here of the theoretical strength divided by the real strength that you observe in practice, and this tells you how far away the real strength is for a given material as compared to its maximum theoretical strength. So this tells you how much weak, how much less tough, how much less strong a material is as compared to its maximum theoretical upper limit of strength. So if you look for glasses, typically glasses are around 80 times less strong than what their maximum theoretical strength would be, but that's not something that is uncommon. For example, if you look for steel, this is typically even worse. The theoretical strength can be up to 200 times higher than the strength that you get in practice for steel. But if you look for silica fibers, for example, then it's very different. Silica fibers have a practice strength that is pretty close, only 1.3 times lower than the theoretical strength. So in that case, for silica fibers, you have a practice strength that is very high, that is very close to the maximum theoretical strength that such material can have. A very useful experiment to be able to understand what is the origin of the discrepancy between the theoretical strength and the real strength of material is to consider the Griffith experiment. So based on this experiment, the idea is to measure the strength of a selection of silica fibers, glass fibers, in relation to their thickness. So the idea of the Griffith experiments is that you take some fibers, some glass fibers, some are very thin like this, and then you gradually increase the thickness of the fiber until you get some fibers that are very thick. And for all the fibers, what you do is that you apply a given stress, a tensile stress, and you check at for which stress is the fiber going to break, for which stress do you initiate fracture and the fiber break into two pieces. So you measure the strength of the fiber as a function of their thickness here. So what you observe is that if you take a fiber, the thicker it is, if you go from here, the less thick, the more thin, up to the thicker optical fiber, what you observe is that the strength is decreasing quite significantly, and at some point it reaches a plateau and converge to a given value. So this tells you that the thickness of material is a very important property that controls how strong materials are. So what is the origin of this? The origin of this is that in practice, the strength of material, their resistance to fracture, strongly depends on the presence of defects at the surface, and especially the presence of cracks at the surface. So we will see why in a few slides, but the idea being that if you have a very thick material, then you have a very high chance to find some defect on the surface, some small cracks that exist on the surface. But if you have a material that is less thick, then the chance that you can find a long crack is much smaller. Otherwise, the material would be broken already. So you will have only small cracks at the surface. And finally, if you have a very, very thin material, again, the chance to find a large defect on the surface becomes even smaller. So you will find potentially some flaws on the surface, some cracks existing on the surface, but necessarily those cracks will be very small because the sample itself is very thin. That being said, at some point, if you keep increasing the thickness of the fiber, at some point the crack will not grow anymore. At some point, the roughness of the glass surface will not increase more, so the size of the flows will not change anymore, and that's why you will have eventually a plateau. So what we see here is that the size of the flows that exist on the surface of glasses is very important property to control their strength. If you have here very small flows at the surface, then you will get a very high strength. If you increase the size of the flows, then the strength is going to decrease. But at some point, as the material becomes thicker and thicker, the size of the flows at the surface is not changing anymore, so that the strength in practice is not changing anymore. So why are the surface flows so important to control the strength of material? Why? Because they tend to concentrate the stress. So for example, if you take a piece of glass and you apply a longitudinal stress here, so you try to break this material by applying a longitudinal stress. If you have an initial flow here at the surface, a small crack at the surface, then it means that the stress here will be very highly concentrated here in front of the crack tip. So here, in front of the flow that is present within the material, you will have a very strong stress concentration. So if you have only small flows, then the stress concentration is not going to be that much. But if you have very large flows, then you will have a lot of stress concentration. So here it means that the level of concentration of the stress will be very intense. So that's why in practice, although the stress that you apply here on top and bottom of the glass sample is always the same, depending on the size of the surface flow that are present at the surface of the glass. If the flows are very large, you will have a large stress concentration. In that case, the material is very likely to break when you have a large stress concentration due to large flows. If you have only low flows, then you have only small stress concentration. And if the stress concentration is smaller, then you will have a lower chance of fracture, a lower chance to break. So the strength tells you what is the force that the material can sustain before it breaks. But in practice, it's very often more useful to know what is the energy that the material can sustain before it breaks. So this is the first description of the fracture mechanics of material. This is the energy approach. The idea is to determine what is the energy that is needed for a given material for cracks to start propagating within the material. So here we are going to consider linear elastic fracture mechanics, which is the description of the propensity of material to break for brittle material. So the idea of this approach is to say that if you have an initial crack within a given material, then potentially you might have here in front of the crack tip some area within the material that deforms in a plastic way. So you might have some irreversible deformation occurring very locally in front of the crack tip. But if the size of this plastic zone here where plastic deformation occur is very small as compared to the size of the material, if the size of the material itself is much larger than the plastic zone, then you can typically neglect this plastic zone, and in that case you can describe the material as being fully brittle, and in that case this is the case of applicability of linear elastic fracture mechanics, which we are going to slightly discuss in the following slides. So first, when you consider the fracture of material, there are very different ways that you can break material. The first one, which is typically the easiest way to break a material, although that depends on the type of material, is to do a mode 1 deformation. So for example, you apply, in that case, you have an initial crack like this, and you apply a load that is orthogonal to the crack tip. So you can try to think about this by if you take some a pair of chopstick that would look like this, and you try to separate the two chopsticks from each other by applying a load that is orthogonal to the surface that separates the two chopsticks. In that case, at some point, as you increase the force to try to separate the two chopsticks, it will be very easy to separate them from each other. It means that you will have a crack that will propagate here from this point until the two chopsticks are separated from each other. So this is the first case. This is the mode 1 fracture of materials. The second mode is the mode 2. Then in that case, the idea is that instead of trying to separate the chopstick by applying a load that is orthogonal to the surface, now to separate the chopstick, what you will try to do is to apply a load that is not orthogonal, but that is in the same direction as the plane that separates the two chopsticks. In that case, this is the mode 2 fracture. And typically for chopstick, for example, it will be much harder to separate the two chopsticks from each other in that case. But at some point, by applying this kind of shear force here, you will be able to initiate a fracture at this point and separate the two chopsticks from each other. And finally, the last mode is the mode 3. In that case, again, you apply a shear deformation, so which is in the same plane as the plane that separates the two chopsticks. In that case, you apply a load. You take one chopstick to the right, one chopstick to the left, and you try to separate the two chopsticks like this. Typically, this mode 3 is harder than mode 1, but easier than mode 2. So if you have any chopstick, you can try to break them like this, and you will see that mode 2 is typically the hardest way to separate two chopsticks from each other. Then to describe what is the energy that a material can sustain before it breaks, the idea is that you will consider first that you have a crack that is propagating. What does it mean that a crack is propagating? It means that you have a crack that has an initial length A, and the crack is increasing. It means that the crack goes from A up to A plus a small increment dA. So the crack is slightly increasing by a distance dA. So this is the situation where you have a crack that is propagating. So here we are not trying at this point to calculate what is the energy needed for a crack to propagate, that is to say for the fracture to occur within the material. Here we are assuming that we have a crack propagating. We have a situation where the size of the crack is increasing, and we are trying to describe what are the different variations of energy that occur within this material. So when you have this crack propagating, the first thing is that what is the energy that is provided to the system? If the system is breaking, it means that you are providing some energy to the system. This is the energy that is used to break the system. So what are you providing? Here you are applying a stress to the material. So you are providing some mechanical energy to the material. So if you try to break this material, what you will do is to increase the mechanical energy that you are providing to this material. So you will provide a small variation of mechanical energy. This is the energy that you are trying to transmit to the material to break it. So now the next question is, what is the material going to do with this energy? So we know from the first law of thermodynamics that the energy is conserved. So if you are providing some mechanical energy to the glass or to the material that you are trying to break, this material must be converted into something else. And this material is going to be used for different things. First, the first thing that can occur is that you are providing some mechanical energy to the system. The first thing that can occur is that this mechanical energy will be transmitted to the material as an internal energy. So you can have, as a first possibility, an increase in the internal energy of the material. So the internal energy is the energy of the atoms, the way the atoms interact with each other. This is the first thing that can occur. If you apply a mechanical load, you transmit some mechanical energy to the material. the first thing that can occur is that this energy is transformed into some internal energy within the material. The second thing that can occur is that the crack will propagate. What happens if the crack is propagating? If the crack is propagating, it means that you can have an increase in the surface of the material. If you have a crack that is propagating by a distance dA, it means that you are going to create some new surface here. And creating some new surface is costing some energy. Why? Because before, when the system was fully connected, when the material was cohesive, the atoms were connected to each other. If you create a new surface, it means that now the atoms of the top surface are not connected to the atom of the bottom surface anymore. So here you used to have some atoms that used to be connected, and now they are not connected to each other anymore if you create a surface, if you increase the size of the crack. So if you increase the size of the crack, what you will do is you will lose some surface energy. So this is the second thing that can occur if you provide some mechanical energy to the system. The first thing is that this system can create some internal energy, or you can have some new surface that is created. So in that case, you will lose some energy. Some energy will be dissipated to create a new surface. Then what can happen next? The next thing that can happen is that you may have some energy that is dissipated. So you can have some energy that is dissipated. There is different way you can dissipate some energy through plastic deformation. For example, if you have a plastic deformation, some necking of the material, some irreversible deformation, it means that the material will deform. This will cost some energy, so some energy will be released, but this is not going to cause the fracture of the material. This is just going to dissipate the energy through some plastic deformation. So this is the part of the energy that is going to be dissipated. And finally, the last thing that can occur is that if you provide some mechanical energy to the system by applying a load, the last thing that can occur is an increase of the kinetic energy of the material. That is to say, if the material is increasing its temperature, that if the temperature is increasing, then it means that some of the mechanical energy that you are providing can potentially be used to increase the temperature of the material. So those are all the different energy contributions that can be used by a material if you provide to this material some energy in the form of a mechanical energy. So if you are considering a brittle material, if you're considering that the material is fully brittle, then what we can say is that there will be no dissipated energy because there is no plasticity, no ductility in brittle material. So it means that this term is zero. And there will be also no increase of temperature. The energy that you will be providing to the material will be used to break the material, not to increase the temperature of the material. You don't have any loss of energy through an increase of the temperature of the material. So those two last terms can be neglected in the case of a brittle material. So if you divide all those energy terms by dA, which is the increase in the crack due to the mechanical energy that you are providing, you can write this expression here. So you are providing mechanical energy dUE, a small mechanical energy. The effect of this mechanical energy is to increase the crack length by a small value dA. And in that case, those two terms can be neglected. They are both equal to zero for a brittle material. And the mechanical energy that you are providing will be used to either increase the internal energy of the material or to create a new surface. So this energy can be either used to increase and can be either transformed into an internal energy within the material or can be used to create a new surface. So altogether, you can rewrite this expression as follows. And here we are going to define a few quantities. First, we are going to define what is the lateral extent of the crack. So for example, if you take a given material like this and you're trying to break it. So you have an initial crack like this. So A is the length of the crack, and we are also going to define here B, which is the lateral extent of the crack. It means that the area of the crack, the surface of the crack is equal to B times A, the lateral distance, the lateral size of the crack and the longitudinal size of the crack A. So those two, the product of those two quantities give you the surface of the crack, the surface of the flow that is present within the material. So based on that, we can define, the first thing is the energy release rate. What is the energy release rate? It is defined as follow. This is the variation of mechanical energy that you are providing to the system minus the energy that is used to increase the internal energy of the system divided by B times dA. And B times dA, what is B times dA? It is the increase of the area due to the crack propagation. The area of the crack before the crack propagation is B times A. If the crack is increasing from A to A plus dA, then it means that you have an increase, a small increase of the area of the crack from being BA up to BA plus B times dA. So the increase of the crack is B times dA. The increase of the surface of the crack is the lateral extent times the small increment dA. So this product of B times dA corresponds to the new surface that is being created if the crack propagates and elongates from over a size dA. Then the other property that we can define is the crack resistance force. The crack resistance force is defined as follow. It is the energy that is used to create the new surface times again the product B times dA, which is the new surface that is being created. So this property can be written as 2 gamma, where gamma is the surface energy of the material. The surface energy of a material is the energy that it costs to create a new surface within the material. So pretty much like the crack resistant force, it's also the energy divided by the surface, but here you have a factor 2 of difference. Why? Because every time you are increasing the size of the crack, you are actually creating 2 surfaces. Here, if you are increasing the surface of the crack, you are creating a top surface and a bottom surface. You are creating a surface for the top chopstick and you are creating a surface for the bottom chopstick. So the new surface that is being created, if you take a given material and add a crack surface in between, then the two materials are now separated from each other. In that case, you have created 2 surfaces, and the total area of those two surfaces will be 2 times the area of the crack. So if you take the area of the crack, the surface that is being created is always 2 times the area of the crack. This is why you have a factor 2 here between the surface energy and the crack resistance force, which is the energy per unit of crack surface. And then, so all those relationships were derived by assuming that you have a crack that is indeed propagating. In that case, by re-expressing this expression now in terms of the energy release rate and the crack resistance rate, you can write that the condition for this crack to propagate is that the energy release rate is equal to the crack resistance force, which is 2 times the surface energy. So what this tells you is that for the crack to propagate within the material, the energy release rate must be equal to 2 times the surface energy. This is the condition for a material to break. the energy release rate, the energy that you are providing to the system, must be 2 times the surface energy of the system, 2 times the energy that is needed to break the system and form a given surface. So the previous equation gives you the condition for a crack to propagate. So this is known as the Griffith criterion. This is going to give you the condition for a crack to increase its length. So the idea is as follows, that if you want to know if a crack will propagate or not, that is to say, if you want to know if the size of a crack will increase or not, what you have to do is to compare the energy release rate to 2 gamma. The condition for a crack to propagate, as we just saw, is that the energy release rate G is equal to 2 gamma. So G is the energy that you provide, and 2 gamma is the energy that is needed for the crack to increase its length, for a new surface to be created within the material. If those two terms are equal, then the crack will propagate. What does it mean? It means that if you look at the value G of the energy release rate, if this energy release rate is smaller than 2 gamma, if the mechanical energy that you provide is such that G is lower than 2 gamma, then there can be no crack propagation. Why? Because the Griffith criterion G equals 2 gamma is not satisfied. You don't provide enough energy for the material to create a new surface. There is not enough energy available for a new surface to be created, so the crack cannot propagate. The length of the crack will not increase. On the other hand, if the energy release rate G is larger or equal to 2 gamma, then the crack can propagate. So this is the Griffith criterion. It gives you a mechanical description that relies on the energy. It tells you how much energy can the material sustain before the crack will start to propagate. So in that case, G is the energy release rate, so it depends on the mechanical energy that you are providing. 2 gamma is the critical energy release rate. Why? So it's the fracture energy, but this is also the critical value. As soon as G becomes larger or equal than this critical value 2 gamma, then crack will propagate. So 2 gamma is also called the critical energy release rate. This is the critical value of the energy release rate for which the crack will propagate. In that case, it means that the condition for fracture to occur, this is the condition for fracture, is that the energy release rate is larger than the critical energy release rate, which is 2 gamma. So this is the condition for fracture. On the other hand, the condition to avoid fracture, the condition so that there is no fracture, so that the material is resistant to fracture, is that the energy release rate is lower than this critical energy release rate, which is given by 2 gamma. If this condition is fulfilled, then there is no fracture that propagates within the material. So it tells you that this term here, the critical energy release rate, or 2 times the surface energy gamma, tells you how much energy can the material sustain before it breaks. So now this is in the case of a brittle material. If you don't have a brittle material, then this relationship, the Griffith criterion, can be slightly changed. In that case, the critical energy release rate, the energy that the material can sustain, or the minimum value of the energy release rate after which a crack will propagate within this material. In that case, this value will be equal to 2 gamma, so this is the same as for a brittle material. But you will also have potentially some dissipated energy if you have a material that is not fully brittle. In that case, the energy that you will need to provide to the system to break it will be equal to the sum of the energy needed to create a new surface, but also the energy that is dissipated within the material, for example, through plastic deformation. So in that case, you will need to take those two energy into account to define the critical energy release rate. But the condition is still the same. Fracture will occur if the energy release rate is larger or equal to the critical energy release rate. This is the condition of fracture that is based on the energy. So this tells you how much energy can the material sustain before it starts breaking. So the energy is the first way to define the resistance to fracture of material. But there is another description of the fracture mechanics of material which relies not on the energy, but on the strength intensity, the stress concentration within a given material. So this is what we are going to briefly describe now. So as we mentioned before, the reason material break in practice and the reason their strength is always lower than their maximum theoretical strength is that in practice, whenever you have a flow at the surface, a crack at the surface, this will induce some stress concentration. The stress that is provided at the boundary of the system is now concentrated over a smaller area, and especially you will have a high concentration here just in front of the crack tip of the flow, the extremity of the flow. So you can calculate here based on the stress sigma naught that you applied here, what is the local stress that is applied as a function of the distance r from the crack tip. So here, if you take a look, you take a distance r from the crack tip, you look at a given distance r, you can calculate what is the expression of the stress on the xy direction and the shear stress. And what you observe is that very small to the crack tip, you have a very high stress value, which actually goes towards infinity. And as you go further away from the crack tip, then gradually the stress decrease and become equal to sigma naught, which is the average stress that you are applying at the extremity of the material. So this stress concentration can be calculated, and it's given by those expressions. It decreases as 1 over the square root of r. So the further away you go from the crack tip, the larger the distance r, the lower will be the stress concentration. And based on that, you can define here a coefficient K1, which is the stress intensity factor, which tells you how much the stress is concentrated at very small distance. If you take the limit for r equals 0 of the 2 pi, the square root of 2 pi r times the stress on the x direction, then you find this value K1, which is the stress concentration factor. So it tells you how concentrated the stress is at the vicinity of the crack. So the unit of this stress intensity factor is not very intuitive. It's in megapascal times the square root meter. Megapascal times square root meter is the unit of this coefficient K1 here, the stress intensity factor. And again, it characterizes how concentrated is the stress in front of the crack tip. The stress intensity factor depends on two things. First, it depends on what is the stress that is applied far away from the flow. So if you apply a stress here that we can write in stress infinity, which is the stress that is very far away. So this is the first term that the stress intensity factor depends on. And the stress intensity factor also depends on the size A of the flow that is at the surface. If you have a very large flow, then you will have a very large stress concentration. If you have a tiny flow on the surface, then the stress concentration will be lower. So what you have different models to be able to calculate this stress intensity factor. For example, if you have a center crack, which is just an infinite plate, if the length of the crack is 2a, then you can calculate the stress intensity factor as the stress that is applied far away times the square root of pi times a, which is the half of the crack length. So you have some other relationship based on the geometry of the crack. If you have an edge crack, for example, then in that case you have the strength intensity factor that is given by this factor 1.12 times the stress that is applied at the boundary of the material times the square root of pi times A, where A is the length of the edge crack in this case. So you have different expression based on the type of crack that is present, based on the type of flow that is present within the material. But in all cases, the strength intensity factor depends on those two things. The strength intensity factor will be higher if the stress that is applied at the boundary is increasing, and the strength intensity factor will also increase if the size of the flow that is present at the surface is increasing. So those are the two things that are controlling the extent of the stress that is concentrated in front of the flow that is present on the surface of the glass. So then in a similar fashion as you can describe what is the energy that is needed for a crack to propagate, you can also look at what is the stress concentration that is needed for the crack to propagate. And the condition is again given by the Griffith criterion, but this time applied to the stress intensity factor. In that case, the condition for a crack to propagate is that the strength intensity factor, which depends on the stress that is applied at the boundaries of the material, but also the size of the flow present at the surface of the glass. The condition for this flow to propagate is that the strength intensity factor K1 is larger than a critical value, which is the critical strength intensity factor, which is also called the fracture toughness. So this corresponds to the critical value of the strength intensity factor, for which the strength intensity, the stress concentration, becomes large enough for the crack to propagate. So you have a condition which is in that case that K1, which is the strength intensity for the crack to propagate, should be larger or equal than K1C, which is the critical value of the strength intensity factor. And this value is also called the fracture toughness. So the first way to describe the fracture of glasses is to say that if the stress concentration, the strength intensity factor, becomes higher than this fracture toughness, then the crack will propagate. This is based on the approach that relies on the stress intensity factor. Or you can use the energy approach, which is to say that the condition for the crack to propagate is that the energy release rate G will induce a crack propagation if the energy release rate is larger or equal to the critical energy release rate. So those two expressions are equivalent to each other, but one relies on the energy that is needed for the crack to propagate. The other one really rely on the strength intensity, the stress concentration that is needed for the crack to propagate. And those two expressions are fully equivalent to each other. For example, here the fracture toughness, so which is the critical strength intensity, so the strength intensity that is needed for the crack to propagate, the fracture toughness, is related to the critical energy release rate. So this critical energy release rate is also related to the fracture toughness. So those two are fully related to each other. Those two approaches based on the energy or the stress concentration are fully equivalent to each other. And the way that you can go from the fracture toughness to the critical energy release rate is by multiplying by the Young's modulus. So in this case, the Young's modulus is the only factor that can be used to relate here the square of the toughness to the critical energy release rate. So those two approaches are fully equivalent to each other. And in both cases, the criterion is that if the strength intensity is larger than the critical strength intensity, which is the toughness, crack will propagate. This is the first condition. Or the second condition is that the energy release rate is larger than the critical energy release rate. This is given by the surface energy in this case. And the first one is given by the toughness of the material. If so, those two conditions, the Griffith condition, if one of those two conditions, which are fully equivalent to each other, is satisfied, then you will have a crack propagation. So this is the condition for having a crack propagation. If those conditions are fulfilled, then the system will break and you will have the crack propagating through the system. On the other hand, if the strength intensity is lower than the toughness, or if the energy release rate is lower than the critical energy release rate, in that case there is no fracture. So those two descriptions are fully equivalent to each other, and it's equally convenient to consider the stress concentration or the energy that is needed for a crack to propagate. So this is why for material, to describe their resistance to fracture, typically you can find two types of property, which is the critical energy release rate, which would be equal to 2 gamma for brittle material, or 2 gamma plus the energy that is dissipated for ductile material. So this is the critical energy release rate, or the fracture toughness, which gives you the critical stress concentration for which the crack will propagate. So those two properties, the toughness or the critical energy release rate, characterize the resistance of material to fracture. The higher the critical energy release rate, or the higher the toughness, then the most resistant material will be. So sometimes the critical energy release rate is also called the fracture energy. This is the energy that is needed for the material to break. And those two quantities, fracture energy or toughness, describe the resistance of material. Again, the higher those quantities, the more resistant material will be to fracture. So this table gives you a few orders of magnitude. So what we see, for example, is that steel is typically a very tough material. So the toughness or the fracture energy is very high, much higher than other materials. For example, if you look at glasses is much weaker. The toughness of glasses is much weaker. This is because glass can have a lot of surface defects that can reduce its maximum, its practical strength. If you look at other materials, for example, wood would be somewhat on the same order of magnitude for the toughness. In that case, the fracture energy is a little bit higher than that of glass. This is because in this case, the stiffness of wood is much lower than the stiffness of glass. If you look at other materials, for example, a metal like aluminum will have a toughness and a fracture energy that is much higher than that of glass. So typically glass, although it is a material that have a very high maximum theoretical strength, its fracture energy or its toughness will typically be very low. This is because glass first is a brittle material, so you cannot dissipate energy through plastic deformation, but also because glass will exhibit a lot of flows on the surface that will tend to concentrate the stress and will facilitate the propagation of cracks, so which will make it easier for glass to break. So if we look a little bit more in details at different types of glasses, so for example, if we look at the fracture energy, for glasses which are brittle material, the critical energy release rate or the fracture energy is equal to 2 gamma, where gamma is the surface energy. In that case, for different glasses, you have different value of gamma. The value of gamma depends on the type of glass that you are considering. For example, if you take a soda-lime glass, typically you will have a slightly lower value than if you take some other types of glasses that are a little bit tougher. But the toughness and the surface energy also depends on the type of atmosphere. Are you trying to measure the surface energy of the glass in just a regular air atmosphere, or in vacuum, or in a special environment that does not contain any water? So in this case, the real surface energy and the real critical energy release rate of glasses will depend on the type of atmosphere that is used. So this is another property that will control the resistance of glasses to material. But typically, whatever is the glass that you consider, the surface energy and the fracture energy will always be fairly small, which means that glasses typically break at low energy. The energy that you need to provide to glasses to break them is typically quite low. So this concludes this chapter and also conclude the CE 105 class. If you have any question about this or the previous chapter, feel free to contact me at my email address, and I'll happy to try to help you out. Thank you for watching.